calcium sea surface temperature from rubers white and pink in the Orca Basin. And I have shown here, I circled in pink the samples from her actual study set in the middle of the graph there. But she is showing that the white rubers represent the mean annual sea surface temperature, while pink rubers tend to represent more of a summer-weighted sea surface temperature. And showing the divergences between these two records could be used to infer changes in seasonality in the Orca Basin. She showed that enhanced seasonality occurred during the last deglacial sequence, and that there was sea surface temperature that was larger, sea surface temperature values that had larger early deglacial warming of nearly 5 degrees Celsius. And she didn't know this was dominated by mean annual trends or winter trends, but there's no winter sea surface temperature proxies to compare in that Orca Basin data set. The next case study that we have was done by Julie Ritchie et al. In 2009, also here at US. And she was looking at G. ruber magnesium calcium sea surface temperature to show that in three different basins, Garrison Basin, Pygmy Basin, which are also in the northern Gulf of Mexico near our sediment trap site. And she's showing that there was about a 2 degrees Celsius cooling during the Little Ice Age in the Gulf of Mexico. And her hypothesis was that this cooling is dominated by winter season cooling. And having this well-constrained winter proxy would help discern how change in seasonality will then play into these past climatic events, like the Little Ice Age. So if only there was a planktic forum that was exclusively in the winter in the Gulf of Mexico. And there is, from our sediment trap studies, we can see that 92% of Globorotalia truncatulinoides, which is this figure here, annual flux occurs in exclusively winter months of January, February, and March. This is our data set from the sediment trap from 2008 to 2014 on the x-axis and the flux data on the y-axis. And as you can see, all of our data is just very exclusively in the winter. The January, February, March flux average is about 130 tests per day, while the entire rest of the year average is only about 4 meters per day. And the red in this graph indicates where we had missing trap cups or no data was just collected, not that there were no forams there. So throughout the presentation, I'm going to probably refer to Globorotalia truncatulinoides as trunks or bugs, just because it's a lot easier to say, and I won't get tongue-tied, just so you guys don't get confused why I'm talking about bugs. So kind of a proof of concept for this project. A USF St. Pete student, Rita Beckhorn, kind of looked at this a little bit, looking at trunks from Thesis Basin and comparing them to Ruber sea surface temperature minus which represents the summer season, minus the winter sea surface temperature, which represents the truncatulinoides. And this was kind of the pilot study. And she showed that throughout time, that winter cooling is dominated by these sea surface changes during the Little Ice Age in the Gulf of Mexico, which is highlighted here in the pink box. But at the time, the trunk depth has not really been confirmed. So can we actually call this sea surface temperature? Prior to this study, the average depth for trunks are about 300 to 400 meters. So the objective of this study is then to determine a depth habitat for the trunks in the Gulf of Mexico and also develop a magnesium-calcium sea surface temperature relationship to then be used in downcore winter sea surface temperature reconstruction. So a little bit about oceanographic setting. Our sediment trap in panel A is located in the inverted yellow triangle at about 27.5 degrees north and 90.3 degrees west. I also have highlighted here a bunch of little clusters of circles, and those are the basins that I had mentioned earlier that the previous studies were done in. That little clump represents Thesis Basin, Pygmy Basin, and Orca Basin, and then the little dot on the further west is where Garrison Basin is located. And using the temperature data from our CTD sites, the average, and also the Hadley data set, the average sea surface temperature at our site ranges anywhere from about 20 degrees in the winter up to 30 degrees Celsius in the summer. Our sediment trap is also affected by the loop current as well. The loop current comes in from the Caribbean Sea, bringing warmer waters, and then it exits out the Straits of Florida. And sometimes warm eddies tend to break off and propagate more north and west upward over our sediment trap site. And while sea surface temperature is what's dominating the seasonal cycle, or sea surface temperature at our sediment trap is dominated by the seasonal cycle, sometimes these small eddies are responsible for short-term anomalies. I also want to point out that the winter mix layer at our sediment trap location is about 0 to 120 meters. So like Julie had mentioned earlier, our sediment trap was deployed in 2008, and it currently is out in the water now. We are actually going out next month to collect and redeploy again at the beginning of July. The trap itself sits about 700 meters below the surface to ensure that we're collecting all of the deep-dwelling Foraminifera at the site in about 1,150 meters of water depth. And there are 21 sample cups that then rotate on a 7 to 14 period, depending on when we set it. And the looking at in the past is just looking at seasonal fluxes on the Foraminifera species. The graph here on the right-hand side is, I forgot to put the x-axis, or the y-axis, I'm sorry, but that is showing total flux for all Foraminiferas from 2008 and the top panel down to 2014. And like I mentioned earlier, all of the red or missing data, or red boxes and arrows indicate no data was taken or not that any data was collected. And you can see, even looking at the cycle here, there tends to be a more higher flux of all species in the winter months, and that is definitely because of the huge influx of trunks during that time. So a little bit about Globorotalia truncatulinoides. This is a keeled, non-spinosed planktic foraminifera. It's commonly interpreted as deep dwelling. Like I said, most literature has an average depth for trunks at about 300 to 400 meters. I really like this image at the bottom left from Caramel et al. That shows a 3D ontogenetic profile of how trunks are adding their chambers. So they add their chambers one by one, and then the final 5 chambers of the adult, which are shown on the bottom panel, represent its adult life stage. And I have labeled those F through F4, where F is the final chamber, and then it goes back inwards. And that'll be important. I'll talk about that later when we do our laser ablation studies. But there are kind of 2 different types of trunks, encrusted and non-encrusted. Now, these are the exact same morphotype, but they just differ in degrees of incrustation. So the non-encrusted form and the encrusted form are the exact same thing. They're just differing with how much crust that they actually have on of them. As you can see, the panel on the right-hand side, E through F, there tends to be little pustules on there. Those aren't exactly crust. Those are what Hemmelben thought to be pustules that are just attachment points for pseudopodia. And then as the species grows and gets older and starts to sink to the bottom of the ocean, it tends to add this crust onto it. So a little bit more about its life cycle. This is an image from Hemmelben in 2005 that kind of shows the average life cycle for all planktic species, but specifically it's showing trunks as well. I've highlighted trunks at the red, and you can see it's one of the deepest dwelling foraminiferas that there are in planktics. And it also tends, so all encrusteds and non-encrusteds, they're the same exact species, and they start their life cycle in the upper water column as a non-encrusted individual. And I refer to this as lamellar calcite. So it all has this lamellar calcite at the top. And then secondary crust, or calcite, or crust, is added at depth to the fully formed adult. So once it gets its final 5 chambers, it starts sinking to the bottom, and then it kind of gets triggered at about 16 degrees. It puts on this crust, which I like to think of as it's getting colder, it puts on a coat of crust to kind of warm it up. Literature then suggests that these individuals return to the surface from below the thermocline to then release their gametes on their annual reproduction cycle. But this is kind of unlikely. We don't really know a lot about this. Different hypotheses have been made. There is an absence of significant upwelling at this area, so it's kind of hard to believe that the trunks can just head back up to the surface. And we really don't know how they're producing or reproducing. Some people have thought that the loop current is perhaps bringing in trunks, but this doesn't really make sense because when we have the high flux of loop current in the summer, that's when we have the lowest amount of trunks and flux in the summer as well. So our best guess now is that perhaps a residual population in the summer is just enough to support 2 orders of magnitude increase in response to temperature. These guys have not been grown in culture yet, so no one really knows that much about their actual life cycle. So the trunks are assumed to be a deep dweller because these studies that have done so, inferring depth habitat from their shell geochemistry, they do so without discriminating between encrusted and non-encrusted. Even though the 2 forms have very different geochemical signals, which is what I'm going to show you today. So not separating the 2 forms, your geochemical changes that you're seeing could reflect changes in the proportion of just encrusted versus non-encrusted instead of actual paleoceanographic changes. So here we present paired isotopic and magnesium calcium measurements on individual non-encrusted and encrusted trunks to do 3 things. To demonstrate that laser ablation ICP-MS analysis of single foraminifera can be used to yield comparable elements to that obtained from solution-based analysis. We want to demonstrate that the non-encrusted form calcifies in the surface mix layer while the crust forms well below the seasonal thermocline, and then also validate a magnesium calcium temperature relationship for trunks. So some of our materials and method, we have picked out 134 trunks based on availability from 2010 to 2014 from our sediment trap. Most of those were non-encrusted from January all the way to December, and then where we could, we got encrusted specimens to compare from the exact same sediment trap cups from January through April. And then our whole shell trunks were then cleaned according to modified procedures for laser ablation. Once dried, then each individual was measured in length and then weighed. So using just our length versus weight, we are able to see this relationship between the non-encrusted and the encrusted forms. I have weight on the y-axis and natural log of the length on the x-axis, and you can see even just looking at the morphometric differences alone, you can distinguish between the two, encrusted, which is in blue, and the non-encrusteds, which are in red. When we were talking about earlier, all of the encrusted non-encrusteds kind of start their life cycle as this non-encrusted individual, and then as they're sinking, they're developing crust. So this gradient between fully encrusted and non-encrusted could actually be hard to distinguish between different foraminiferas. So it's awesome that we now have, just using this morphometrics alone, we can distinguish between the two when visual discrimination is sometimes hard to see. So I mentioned that we did laser ablation instead of solution-based magnesium calcium measurements. We have a low abundance of trunks in the sediment trap and down core material at the site, especially in the winter month, or especially in this non-winter months. So doing typical solution-based magnesium calcium at the USGS on the OES requires about 200 micrograms or 15 individuals, and there's just times of the year where we don't have that much to do that study. So we decided that using a laser ablation might be a better way to go because you only need exactly one individual to do a measurement. That one individual measurement can then give us many continuous measurements throughout a chamber wall and give us insight into the calcification process, which is the main point of this paper, is we want to kind of figure out what is the differences between this crust and this non-encrusted. When you're using solution-based studies, it's obscuring the calcification process when you're having to homogenize multiple individuals. Also with laser ablation, we can get paired magnesium calcium and delta O18 on the exact same individual. I'm not saying that laser is always better, but for this case, for our study, it was better to use laser ablation. So we wanted to compare this laser ablation magnesium calcium versus solution-based magnesium calcium to see how the two values actually compare. So we have plotted here magnesium calcium on the y-axis, and then we have just 6 individuals that were chosen at random from the sediment trap site where we had a lot of samples. And we did compared our laser ablation ICP OES stuff with our our laser ablation stuff with our solution-based stuff. On the graph here, everything that is the clear white boxes are showing our laser ablation data set, and then the solution-based data set is in the pink as well. And 5 out of 6 of our samples do have lower magnesium calcium with laser ablation, but they are within error of one another, and that's kind of the main thing that we wanted to see, is how close we can relate these two. We also compared all of the study from Spirit all 2011, where she did non-encrusted solution work with our entire laser ablation data set, and they again are within error of one another. So while these results are comparable, I also want to point out that with laser ablation studies, it's always best to have more than just 1 or 2 individuals, just so that you can get meaningful environmental information on the population. So we did our foraminifera laser ablation techniques at UC Davis in 2016. We took all of our cleaned whole shell trunks over there. And the trunks, what they look like, they kind of look like triangles. So in order to get, as the laser is shooting through, we wanted to ensure that there's a flat surface. So we placed them all upside down onto double-sided tape so that when we have a flat surface to then ablate our profiles through. The main picture that I want to focus on is the one in the middle showing the different chambers, F through F6, like I had talked about earlier. For our stuff, we ablated then at least 1 or 2 spots in every single chamber as far back as we could go. We wanted to ensure that we knew exactly what chamber we were in and what we were calling it. So for sometimes we just couldn't see the distinction between the chamber wall. So we did an ablate there because we wanted to make sure that we were calling F3 versus F4 and knew what we were doing. The figure on the right-hand side is showing what those profiles actually look like. Each little blip of data is 1 spot of data of their elemental profiles. So as the laser is shooting in through the shell, it is then being measured simultaneously onto the computer. The 2 images below on the bottom are SEM images from the ablated shells that we use, and you can see how the laser ablation goes through the shell. And also, the one in the middle also has a really good picture of how you can see that chamber wall separating the two chambers. The laser was then adjusted for encrusted versus non-encrusted. If we had a very high energy laser going through the non-encrusted form, or going through the non-encrusted forms, it would basically shoot through it so fast that you wouldn't be able to see any of that profile. So we had to adjust that from the non-encrusteds to the encrusteds so we could see what the profile actually looks like. So this is what an example of a laser ablation profile looks like for just one individual foraminifera. We have magnesium calcium on the y-axis, which varies anywhere from about 1.5 millimoles per mole to 8 millimoles per mole throughout time. Time is representative of calcite thickness. The longer that your ablation time is, represents more thickly calcified shell, where if you have a smaller ablation time, that means you have smaller calcite thickness. And as you can see, there's just considerable heterogeneity throughout the entire profile, not only between two spots from the exact same chamber, but also between all of the chambers on an individual. So we wanted to figure out how then to approximate whole shell magnesium calcium. The dashed line shows if you just take the mean magnesium calcium of all the data, but that's not really the most correct way of doing it in this case. So we wanted to weight all of our chambers according to their ablation time, just to get a true representation of magnesium calcium for each individual. The next thing we wanted to do was think about how to remove lamellar calcite from the crust. Earlier I had said that lamellar calcite is kind of like the baby calcite on the individual, and then as it's sinking, it's adding this crust onto it. And we're really trying to get a difference between the crust and the non-encrusted forms. So on the encrusted individuals, we want to then somehow remove that lamellar calcite because we don't really want to take that magnesium calcium data into our encrusted specimen. So we can actually use our length to weight relationship to estimate then the relative contribution of the lamellar calcite to the encrusted specimens. So the picture on the right-hand side just shows an example of an encrusted foraminifera that weighs 700 microns. And using those two equations that we have calculated for the non-encrusteds and the encrusteds, we can determine what the weights then are for that individual of the non-encrusted and of what the lamellar calcite is versus what the crust is on that individual. And on this example, it was 71% is true crust, while 29% comes from lamellar calcite. We did that with all of the individuals, and they average anywhere from 68 to 71% crust. So we also wanted to then do a second method just to kind of test this to be sure. So we then identified secondary crusts in our laser ablation profiles. On the bottom left-hand side, we have the non-encrusted magnesium calcium profiles. We have magnesium calcium on the y-axis and then ablation time on the x-axis. And as you can see, there's that heterogeneity between, these are individual spots for just three random spots throughout the profiles. But then you can see all of the encrusted profiles tend to look a little bit different. Their ablation time is much longer, also because they are thicker as well, but they all tend to have this homogeneous zone inside the middle of them, which is representative of the crust. As you are looking at this profile, 0 kind of represents the outside of the shell, and then as you're going through time, that you're going through the shell, and then the interior of the shell is kind of what you have at the end. And you can see that there is that heterogeneity again on the inside of the shell, which represents that non-encrusted lamellar calcite. So for every single spot, we kind of determined what the average was of this homogeneous zone, and the crust then accounts for exactly the same number of 71 plus or minus 10% of the total shell. So we assume that 29% then of the calcite of an encrusted specimen originates in this winter mixed layer of lamellar calcite. So we have corrected all of our isotopic and magnesium calcium measurements on the encrusted form to then remove that contribution of lamellar calcite throughout the rest of this paper and presentation. And this in turn allows for more accurate estimates of water column conditions during incrustation. So on to our data. These are the isotopic measurements of our delta O18 of the calcite. We have non-encrusted on the left-hand side in red, and then the encrusteds on the right-hand side in blue. As you can see that throughout time, the warmer the temperature, the lower the delta O18 value is. And you can see there's a clear difference just looking at the average. Note that the y-axes are different for encrusteds and non-encrusteds. The non-encrusted average delta O18 is negative 0.32 per mil, while the encrusteds are 1.30 per mil. So they definitely have very distinct geochemical signals between the two of them. So using that delta 018 then, we can determine depth habitat for these guys. The chunk's depth habitat, based on past literature, ranges anywhere from 100 to 800 meters, depending on whether people were doing core top studies, looking at actual plankton toes of collecting these guys. So to determine the calcification depths then for both, we're going to use IFA, which is individual foraminiferal analyses, on the delta 018 of the calcite. So we used 7 different published delta 018 paleotemperature equations that have been used on truncatulinoides in the past, and our CTD data since 2008 to then predict the foraminiferal calcite at the different depths in the water column. So this is a graph showing the delta 018 of calcite on the x-axis, and I have those isotopic measurements that we had seen earlier that were, now I just flipped them horizontally so that we could see them with depth throughout time. And we have January, February, and March plotted here, which are the highest amount of flux, where we have the most amount of non-encrusted specimens as well. And you can see that there's a clear difference between the two, the non-encrusteds in the red and the encrusteds in the blue. I also want to point out that we decided to use all of these equations. Most studies just use 1 or 2 to then get their depth habitat, but we wanted to really show what kind of the most shallowest possibility is for every single month and the deepest possibility. So we, instead of just using 1 or 2 equations, we decided to plot all of them. So this is showing our range and average depth for the chunks throughout time for every single month on the x-axis, with depth on the y-axis. And we have that truncated at 700 meters because that's where our sediment trap is sitting. I also showed in black here the percentage of the flux for every single month in the sediment trap as well. We have our non-encrusteds in red and our encrusteds in blue. Our average non-encrusted depth is 66 plus or minus 9 meters, while the average encrusted depth is 379 meters. I also want to point out that if this data is showing that we had removed that lamellar calcite, if we hadn't removed the lamellar calcite, the average crust depth would be about 250 meters. So it's a really big difference removing that lamellar calcite from the shell. The blue line here represents what the thermocline is at the sediment trap. And when we have the highest amount of flux and in the winter months of January and February and March, our species are the most shallow, living in the shallowest part of the water there, above the thermocline. As the summer months come, they start below the thermocline. So now that we have this confirmed mixed layer depth for our non-encrusteds, we can then use them now as sea surface temperature recorders. So we created our own new equation, which is shown in the thick gray line in the middle of the graph, but we have plotted here our weighted magnesium calcium measurements against our delta 018 calcification temperature to kind of create our own equation, see what's going to be the best fit equation then to use for the non-encrusted forms. We have our encrusted forms are in the triangles at the bottom of the graph, and then our non-encrusteds are the black circles, and we're going to focus on those because that's kind of the species or the form that we most care about. Not that we don't care about the crust, but not really for this data set. So as you can see, it was hard to compare then which actually equation is the best fit. All of these equations were chosen because these are past truncatulinoides studies that have been used for magnesium calcium sea surface temperature in the past. So I wanted to compare all of them and kind of see what is going to be the best fit then for our data set. And the two that are the best fit are the equation that we created, the thick gray line, and then the Anand et al. 10 planktonic species, which is in the thick black line. And that includes a bunch of planktic foraminiferas as well as truncatulinoides in that data set. So looking at comparing the two of these together, both of them have very low residuals using those two equations. And they also have 95% of their magnesium calcium determinations fall within 2 sigma of predicted magnesium calcium. And they also have about nearly identical temperature averages. So it's hard to then decide which of these two is going to be best to use moving forward. But kind of the big what we want to do in the future with this study is then how do these compare in downcore temperature reconstructions? So we decided to then actually use a downcore study to use the two equations and see which one kind of has more of a best fit. So this is using data from Spear et al. In 2010, where she did non-encrusted trunk magnesium calcium in Pygmy Basin, which is near the sediment trap that I had shown earlier. We have magnesium calcium temperature plotted on the y-axis and the calendar year plotted on the x-axis. And using our two equations and her data set, the Anand et al. Has about a 3.2 degrees Celsius trend, and our equation 2, which is the equation that we created for this study, has about a 5.4 degree trend. Both estimates are much larger than the expected observational record from the Hadley data set, which is only about less than half a degree Celsius, which is a little disconcerting, but different proxies from the Sediment Trap study have also been shown to have larger than expected trends. Tex 86 sea surface temperature and G rubra magnesium calcium sea surface temperature during this exact same time period shows trends of about 1.1 degrees Celsius and 1.4 degrees Celsius. So if we think back to the study that Rita Beckhorn had kind of started with her pilot study and the study that Julie Ritchie did with the Little Ice Age, cooling is dominated by the winter season. So perhaps winter sea surface temperature just has larger interannual variance than the summer or mean annual sea surface temperature in the Gulf of Mexico. Even though both equations are very similar, our equation that we created kind of has unexpectedly high trends. So we decided that the Anand et al. Is going to be the best equation then to use moving forward for the non-encrusted magnesium calcium paleo temperature reconstructions. So kind of our big take-home figure, using that non-encrusted data set and the Anand et al. Planktonic species equation, we can plot temperature then on the y-axis through our time series on the x-axis. And you can see we also have plotted here then the Hadley data set, which is shown in the light gray line. So the average temperature for Anand et al. Is 21.3 degrees Celsius. And then comparing